for that, we're very pleased to have Hannah Schwartz telling us about regular homotopies and Glock twists.
Okay, well, thank you guys. Thank you for inviting me. And I'm sorry we've had such a crazy week and I haven't really made it too much. But yeah, there's like an awesome lineup of people here. So I'm very impressed. And I bet you learned a lot. So hopefully this will, I don't know, reference a lot of the things that other people have talked about. So it'll be like a good wrap up. So yeah, I wanted to mention at least, so there's at least two things that this talk is going to directly relate to in terms of like a wrap up. So there was two lightning talks in particular I wanted to give a shout out to. So first of all, there's Ben Rupik's lightning talk. So he talks about this paper that's joined with me, Jason Joseph, Mike Klug, and then Ben, called Unknotting Numbers of Two Spheres in the Four Sphere. So that's sort of what he was talking about in his little 5-minute lightning talk. And then Patrick Naylor also has a lightning talk that's up there that's talking about this paper, Glock Twisting Roll Spun Knots, which is just him and me. So basically what I wanted to do was, possibly expound on some of the things that were in their two lightning talks and then kind of also bring them together. Because I sort of, these papers came about like a couple years ago and I was sort of working on both of them more or less at the same time. So there's sort of two different things happening in them, but they kind of the paper with Patrick kind of relies on the one that I did with Jason, Mike, and Ben. So I want to kind of like explain the relationship between these two papers as well. Okay, so the structure is we're going to have story one, which is the first paper. Story two is the second kind of paper and topic. And then kind of at the end, we'll kind of mush it all together and see how one relates to the other. Okay, so first of all, just kind of a general question to get us started talking about. So I don't know, maybe a good question and maybe you have some ideas for its answer is, what are some good measures of the complexity of knotted two spheres in S4? Right. So I'm just going to already specialize to knotted two spheres in S4, so I don't have to write as many like qualifying words sometimes. You could obviously like have a nice question that's just for surfaces in any four manifold as well. Still interesting. But anyways, so let's just think about knotted two spheres in S4. And by the way, for this whole talk, you probably know already from some of your lectures that it's important here to clarify that I'm talking about being a smoothly knotted two sphere and thinking about a smooth structure on S4 as well, right? Because the topological and smooth categories are different. So yeah, everything's going to be smooth here as well. So I don't know, to give us sort of like a feel for like maybe some good measures of complexities of two spheres in S4, I wanted to sort of, maybe first think in 3D, what are some kind of good measures that we kind of have had for a while for just regular knots in S3 first. And then we'll kind of jump over and see how well, or maybe how not so well, they kind of work for knotted spheres in S4. Okay, so I have some things you'll probably like recognize in this column, and then we'll like fill this in kind of together as we go. Okay, so I guess the first measure of complexity that like popped into my head at least for a knot in S3 was the fundamental group of its complement. So you can certainly obviously do this as well for knotted two spheres. So you can look at pi1 of S4 minus the knotted two sphere K. And that can definitely be super interesting and actually even more interesting than fundamental groups for knots. So they include all the fundamental groups for knots plus more things. So that's very cool to look at. So in one sense, they're like a good measure of complexity, obviously, but there's also sort of some faults here because we might have two different two spheres with the same fundamental group. So even maybe there's an unknotted two sphere with fundamental group Z or something. So it's not particularly good at just like identifying a unique two sphere maybe. So there's good things and bad things with this. Fine. Okay, so second thing I kind of just wrote for us to just think about, I guess, is the three-ball genus of a knot. So, you take your knot and take a cipher surface that it spans, and you want the minimum genus of such a cipher surface. So, for a knotted two sphere, well, this two sphere K in S4 also bounds a Seifert manifold, right? So it's a 3 manifold this time with boundary, that 2-sphere. So you could look at maybe, you know, there's not really a genus that makes sense, but you could look at some invariant associated to the Seifert manifold. Okay, but you know, it's unclear sort of what the best invariant is of the Seifert manifold to choose, like, you know, which ones are sort of meaningful to the knot on the boundary and which aren't. So, you know, a few of these sort of next two invariants that I want to talk about down here are sort of picking out maybe like, you know, different sorts of invariants of these like Seifert manifolds or even like immersed manifolds bounded by it. So, okay, I want to start by thinking about the band unknotting number of a knot. So this is again for a knot in S3. So, right, so what you do is you take, again, I guess to see it first, I like to think of the knot as bounding this Seifert surface. So this is a genus 1 Seifert surface that I drew just kind of abstractly for some knot. And now, you know, you can kind of go along and remove some bands from the Seifert surface so that at the end, you sort of only see a disk bounded by the knot together with those bands. I don't know if I said that very clearly, but you can sort of see it maybe better from the picture than from what I'm saying. So once I take the knot and I add on these bands, now this knot on the boundary is actually an unknot, right? So it bounds a disk in S3. So the band unknotting number, so, you know, at least this gives you some sort of like an, you know, an upper bound for how many bands you need to sort of attach to K to get an unknot. But, you know, you might be able to do better than that. And a minimum over how many bands you need to attach to get the unknot is called the band unknotting number. Okay, so I want to sort of carry that over to see what that's kind of a, to get a similar idea for knotted 2 spheres in S4. Okay, so hold on, I want to see my notes on this screen. I have to fiddle around with my computer for a second. Let's do this. Okay, I want to see all of you and I want to see my notes at the same time. Okay, so right, so the kind of the 4D analogy of this band unknotting number is called sometimes the stabilization number, and written, so it looks kind of like U for like an unknotting number kind of, and then ST for stabilization of the 2-sphere K. Okay, so this essentially means sort of, you know, I have my knot K. So I'm knotted 2-sphere now, and it's the minimum number of little tubes like this that I can sort of attach to K. And these tubes, you know, here, I don't really have much space to draw anything too exciting, but they may kind of wrap around like K, you know, in the fundamental group of K might be interesting. So you might have really interesting tubes that aren't like equivalent to one another. But it's the minimum number of tubes you can attach to get sort of an unknotted genus G surface. So one that bounds a handle body in S4. Okay, and how do we know that, you know, some number of tubes has to do it? So just like we knew over here, you know, we want to know whether or not these numbers are well defined. So we need to know that there's at least some sort of like a max, there's some sort of upper bound. So here we got this upper bound by looking at the Seifert surface of K. And over here, we can do the same thing by looking at a Seifert manifold for the 2-knot K. So again, I'm going to draw like a schematic. So I have the 2-knot K, and in S4, it bounds some Seifert 3 manifolds. Okay, so that Seifert 3 manifold, I can think about, you know, as having some sort of a Haggard splitting, or if you want like a Morse function on it. So I can see the 0 handles first, and then 1 handles. So maybe, you know, there's like 5. So, I mean, you need to get sort of something connected at the top. And we're assuming this 3 manifold's connected. So I need at least as many 1 handles minus 1 as 0 handles, but then I may have more. Oops, wait, there you go. All right, and then I also need basically an equal number, maybe, or no, I could have whatever, some number of 2 handles. Okay, so if you kind of look in the middle here, this is some sort of like a Heegard surface, basically, for this punctured 3 manifold. So in particular, this part below is a solid handle body. It's just like 3 balls union these 3-dimensional 1 handles. So it's a solid handle body. So this surface here is actually the unknotted surface. That is a stabilization of the 2 knot K, right? Because to K, I can think of it as adding these sort of tubes that are like kind of the result of this like cobordism from here to here, right? So this here, like this solid thing is sort of the 3-dimensional 2 handle, but like flipped over upside down. So it looks like you're adding a 1 handle to K. Anyways, so the point is, you know, both of these are sort of well defined for the same reasons, and it's really like the exact same notion. So here you're adding like a band onto the knot K, and here you're adding on a little tube to the 2 knot K. Okay, so kind of analogous. So, you know, this was also seems like an interesting object of study. So like, you know, it measures the complexity somehow of this 2 knot K. How far away is it from like an unknotted surface of some genus? Okay, so, right, the very last thing I wanted to bring up, and maybe I should go a little faster so we can actually get through this talk. So is the unknotting number of knot K. Okay, so one way to think about this, I guess, is the minimum number of double points that you see during a homotopy to the unknot from your knot. So the number of crossings you need to change to get to the unknot, basically. So again, there's sort of an analogous notion for a knotted 2-sphere in S4. And what we'll call this is the Casson-Whitney number of the knot. And I'm going to write, again, a U for an unknotting number. And then CW for Casson-Whitney of the knot K. And what this is the minimum number of positive and negative pairs. So they're going to come in pairs rather than just these single isolated double points. So of positive and negative pairs of double points that arise during a homotopy from K to the unknot. And here I mean the unknotted 2-sphere, so it bounds a 3-ball. Okay, so why is it called Casson-Whitney number rather than kind of a knotting number? Well, because basically during a homotopy from a 2-sphere to the unknot, or at least during a nice regular homotopy, you can sort of only see 2 things locally. So, you know, one is you can see the introduction of a pair of double points of opposite sign. So I can go from here to here over time, and I see 2 additional points. So that in some sense contributes 1 to the Casson-Whitney number. I do mean regular homotopy, yes. So, you know, or the other thing is you can see sort of the inverse of this process. So you can cancel a pair of double points. Okay. So this direction, canceling the pair of double points, has been thought about since Whitney. So it's called a Whitney move. And then the inverse of this is often called a finger move, because it looks like you're kind of taking your finger and poking one part of the surface through the other part. And this was sort of like, I guess, explored and exploited the most by Casson in the 70s. So this is why we sort of attributed it to him. Okay. Great. Okay, so these are sort of 2 interesting invariants of 2 spheres that kind of measure their complexity that I happen to be interested in. Okay, so you know, this paper with Jason, Mike, and Ben, we kind of explore the relationship between these 2 invariants, because in some sense you can think of both of them as like some sort of an unknotting number of the 2-sphere, and we wanted to sort of know, you know, is one always bounded by the other and such. So, you know, algebraically, a lot of stuff goes on that suggests one should be strictly, or one should be less than or equal to the other. But unfortunately, like we talked about up here with the fundamental group, the algebra doesn't always like translate to the geometry in the smooth world. So yeah, there's sort of some open questions lying around in there. So I encourage you to go look at our paper if you're kind of interested. Anyways, I wanted to point out 2 results pertaining to this that are in our paper that are going to come up a little bit later. So one is that actually the stabilization number of the 2-sphere is always less than or equal to the Cass-Whitney number plus 1. So sort of unfortunate, you would love to like not have this +1 here, and it's sort of unclear if we need it all the time, but the only thing we could actually prove is this inequality with the +1 added. So right, so Cass-Whitney is sort of almost an upper bound for the stabilization number. But we were able to get sort of an equality in the case where the Cass-Whitney number was equal to 1. So if there's a regular homotopy from your knot to the unknot that has only 1 finger and 1 Whitney move, then you can actually stabilize the knot to get an unknotted torus. Okay, so this result in particular is what I'm going to end up referencing later at a certain time. So commit that to memory, you will be quizzed. All right, great. All right, I have to go so fast now because I could just talk forever. So story 2 is about Patrick's lightning talk. Okay, so Glock twisting rolls but not. So I got to tell you kind of what's a Glock twist. I'm sure a lot of you already know, but we're going to do it. So let's see. I have a knotted 2-sphere in S4, and I can kind of obtain a possibly different 4 manifold by removing the tubular neighborhood of K. So that tubular neighborhood looks like S2 cross D2. I can remove that and reglue it by some map on the boundary of that tubular neighborhood, right? So the way the manifold that I sort of get as a result, so this manifold over here on the right, obviously depends on the gluing map you use. So it depends on some automorphism of the boundary of this tubular neighborhood. Okay, so the boundary looks like S2 cross S1. And actually, you know, kind of conveniently, I guess, Gluck in the 60s, Hermann Gluck, showed that up to isotopy, there is really only one non-trivial, so not equal to the identity, orientation preserving map on S2 cross S1, and we'll call it tau. So tau is this important map, so tau for twisting, and so it's called usually like the Glock twist. So if I remove and reglue the neighborhood of this knotted 2-sphere and reglue it using tau, using this map tau, so I think Patrick actually like defines this a little more explicitly in his lightning talk. Then this is called doing a Glock twist on the 2-sphere, and the resulting manifold, which may or may not be equal to S4, is also called a Glock twist on the knot K. So it's kind of like a verb and a noun at the same time. Okay, so you know, because we're doing this on a 2-sphere in S4 by Friedman, oops, by Friedman, this manifold is actually homeomorphic to S4. Right, so if I'm in a general 4 manifold, this is not necessarily, the resulting manifold is not necessarily homeomorphic to the initial one, right? You can actually change H2, but since I'm starting with a 2-sphere in S4, in particular, it doesn't. So I'm good by Friedman. So you know, because of this construction, the Glock twist has sort of like become a big thing because it gives you a lot of sort of potentially exotic 4 spheres, right? So you're searching for a counterexample to the 4-dimensional like smooth Poincare conjecture. So this is a really good place to kind of start. It's a very concrete way, and you can, you know, draw a really nice Kirby diagram of it to get some like potentially exotic 4 manifolds. So a lot of people have spent a lot of time trying to show that certain Glock twists are or aren't standard. Okay, so a related surgery that you can do on a 4 manifold, I don't know whether or not you talked about this at all this week, is you can do something similar, but instead of a 2-sphere, you can do it with a knotted torus. So any torus sitting in S4 also has a trivial normal bundle. So it looks like T2 cross D2. And again, I can remove and reglue that tubular neighborhood by some map on the boundary. So the boundary here looks like T3, looks like S1 cross S1 coming from T2, and then the S1 on the boundary of the normal disk. So this will give you another torus, and again, a possibly different 4 manifold. And now, unfortunately, even though it's in S4, it can actually change homology, and so you may not end up with something homeomorphic to S4. So in order to guarantee that we do, I want to introduce kind of a focus on a special case of this. So a special case is when you see the gluing map. So it's going from S1 cross S1 to S1 back to itself. And suppose it kind of sends the very last meridian. So I'm kind of writing it a little informally like this. So it's just the curve going once around this last copy of S1. Suppose the map sends that circle to something that looks like, any multiple of the first 2 circles, but just a single one of the last one. So it's still kind of 1 in the last spot. This is called the multiplicity 1 log transform. And in this case, if you do sort of the log transform of the torus using a multiplicity 1, using a map of this form, then what you do get is something homeomorphic to S4. Okay, cool. So these 2 notions also sort of relate to one another. So Gluck twisting a 2-sphere versus doing a log transform of multiplicity 1 on a torus. So there's 2 theorems I'd like to point out. So one theorem is due to Montesinos in the 80s, and Kyle Larson actually gave sort of a newer proof of it in 2018. So, right, so first this is just addressing sort of this bottom surgery. So if you have a multiplicity 1 log transform on an unknotted torus in S4, then it's standard, meaning it's diffeomorphic to the 4-sphere. Okay, so this is interesting because, right, A and B, these 2 coefficients can sort of be anything. So, this map can be like vaguely interesting. And so maybe, it wasn't like just super straightforward to just know that this thing is already S4, but in fact it is. Okay, so the second theorem is one that was also initially proved in the 80s by Awasi. But in Patrick and my paper, we sort of also offer like a new proof. So there's sort of this parallel. Both of these were sort of first stated in the 80s and proved in like a more modern way, I guess, more recently. But this relates these log transforms of multiplicity 1 to Gluck twists. So if you have a Gluck twist on a sphere in S4, then that Gluck twist is diffeomorphic to a multiplicity 1 log transform along any one of its stabilizations. So if you stabilize the 2-sphere, so you add a little tube to it, you get a torus. And it's not necessarily, it's not necessarily an unknotted torus. But you can still do a log transform of that torus. And there's some multiplicity log transform on that torus that is diffeomorphic to the Gluck twist of that 2-sphere. Okay. Great. So this kind of relates those 2 stories together. Okay. So now, like we said, because of Friedman, the fact that we're doing this Gluck twist on a 2-sphere in S4, we can generate these potentially exotic manifolds. So that's kind of the exciting thing about this construction. So there's this question that's still open in general. Is the Gluck twist of any 2-sphere in S4 diffeomorphic to the 4-sphere? So is it still standard? So although it's still open in general, it is known to be true. So I guess, so there are a lot of spheres that are known whose Gluck twists are always standard. So certain families. So I just wrote a few of the kind of first ones that came to my mind. There are certainly like others that people have wrote down. So there's ribbon 2-spheres, for instance. There's Artin spun knots. So there's a family of knots called spun knots you may or may not know of. Zero concordant knots is another family that's known to be have standard Gluck twists for a while. Also twist spun knots are known to have standard Gluck twists. And again, maybe notice the dates here that these have been known to have standard Gluck twists for quite some time. So one sort of interesting family of two spheres, which this is unknown for. So you see here, there's spun knots, and down here, there's these twist spun knots, kind of like a generalization. So there's kind of an even larger generalization due to Litherland. So he defined something called deformed spun knots, which kind of encompass all two of these. And these also include a family of knots called roll spun knots. Okay, so these are unknown to have trivial Glock twists. And it's kind of why I started thinking about this question in general. Okay, so what Patrick and I were able to prove was basically adding something to this list. So we were able to show that if you had two spheres with stabilization number 1, then their Glock twist would also be trivial. So this is by Patrick and I. And this was like last year, I think. Okay, so we add this bullet here. Okay, so fine. I wrote it as a separate line, but that doesn't necessarily mean this actually adds any new two spheres. Like, you know, maybe only these two spheres have stabilization number 1 or something. I don't really have much of a concept whether or not this like adds anything to the list. So, you know, is there anything new? So I guess the question is, you know, which two spheres have stabilization number 1? So there's a few that are known. So spun knots do, but you know, spun knots are already up here on the list. So that's not super exciting for us. Twist spun, or okay, I shouldn't say spun knots. Spun knots of 1 knots with unknotting number 1. Okay, and then same here for twist spun knots. Okay, also some like simple ribbon two spheres, and simple here is in quotes. So just, you know, with a small number of tubes maybe. So some ribbon two spheres also have stabilization number 1, but so far all of these knots are sort of already up here in my list. So what Patrick and I also were able to add here was that also roll spins, again, of knots with unknotting number 1, copy, paste, have stabilization number 1. So this actually adds something, you know, new to this list, and consequently to the list above as well. So up here now, we weren't able to sort of answer this question for all roll spun knots, but we were able to answer it for kind of small roll spins in a certain sense. Okay, so roll spins at least sort of with stabilization number 1. Okay, it's about 1:50, so I could definitely elaborate, but I'm gonna let it go for now so you guys can have a nice weekend soon. Thank you so much.
All right, let's thank Hannah. Are there any questions?
I had a question. Hannah, can you go back up to the first page?
Definitely. Okay.
I think you said something like this out loud, but I think I missed it. So, you know, for in the 3-dimensional setting, you know, the like knots are determined by their complements theorem. And so what is like known at all as like an analogy analogy to that theorem in the 4-dimensional setting for 2 knots? Like what's the best that we know?
Okay, I'm gonna need people from the audience to like help me fill in, because I definitely do not know everything about this. So I think there's some more stuff known maybe for like higher genus surfaces. Maggie, you should help me answer this too. I don't really.
What was the question?
I just said, you know, I said, you know, in 3 dimensions, we know like knots are determined by their complements, the Gordon-Luecke theorem. And so my question was like, what's the best that we know in analogy to that theorem for the knotted surfaces, knotted two-sphere setting?
And Hannah, you said they come in pairs usually, or
no? So well, I mean, first of all, yeah. So first of all, there is sort of the issue of so you may have actually like there are examples where there's like two distinct knots with the same complements. So they're definitely not determined by their complement.
Oh,
So
okay,
like,
okay.
yeah. So for instance, like if you have a knot, and there are examples, I think like for some of the twist spins or something, it can Gluck twist to give you the 4-sphere. But so down here, you know, when you do the Gluck twist, you have your knot that you're starting with, and then you do the Gluck twist. So maybe you end up in S4, but this knot in here is not the original knot in S4. So that happens sometimes where they have the same complement, but sort of when you do a Gluck twist on one of them, you end up at S4 containing the other one, kind of. So it's a little
Oh,
weird.
I see.
And
And who's the right
also-
reference for that?
so I would look at Cameron Gordon's thing.
He has a paper called Unknotting in the 4-sphere. And he has
Yeah.
explicit examples of both kinds.
Oh,
yeah.
cool.
But then I think what I kind of said out loud too was just talking even just about kind of the fundamental group of the knot. So because of that, you know, because of this example, you can see that the fundamental group does not really determine the 2 knot. But I mean, even just, you know, for the unknotted 2-sphere, you know, are there any sort of smooth 2 spheres with complement Z or something that are not the unknot? Yeah, it's sort of unknown, like what happens with the fundamental group, and that causes like a lot of trouble.
Great, thank you.
Yeah.
Are there any further questions?
I was going to ask a kind of a related question. Do you know like a good description for the Gluck twists of the, or the for the 2-sphere that you get by Gluck twisting the things that you proved were standard? So like, for example, with twist spins, like there's like a good description of the Gluck twist, which is like the branch twist spins or something like that. But presumably there's not something similar for these roll spins that you
I don't know. I mean, like obviously, you know, you could draw like a Kirby diagram for it.
Sure.
I'm not sure about some sort of like, I don't know, more general way of describing it.
Yeah, just like I meant like a more, yeah, not a more explicit construction, but like a more, I don't know, on its own construct. Yeah, separate construct.
I don't know off the top of my head, but that does not mean it does not exist.
Sure.
Any further questions?
Have you ever thought about these spheres with higher unknotting numbers, like a 2, 3, 4?
Yeah, so we were thinking about this for a while. So one of the contexts in which this is interesting, I guess. So it's odd because sort of the struggle that Patrick and I had to extend our construction here. So we wanted to show, so okay, you know, somehow, okay, let me think of how to say this to you. So, right, I guess the root of the problem is sort of like here. So, you know, we kept having to get this +1, and kind of one of the reasons why is because, you know, to go from a regular homotopy to stabilizing the knot, there's sort of like a good way to go from one to the other, but there's an issue to know sort of what the isotopy class of that stabilization is, like how they're related based on sort of the, okay, so in the regular homotopy, you have a bunch of kind of finger discs and Whitney discs. So these kind of describe to you what the regular homotopy looks like. And, you know, if the boundaries of these discs are different, it sort of really upsets our story with the stabilizations. So I don't know. So somehow like relating these two things is also sort of why like Patrick and I had trouble like extending our proof to like higher, I guess at least like unknotting numbers. You know, it's hard to do this for stabilizations or for stabilization number. Like I would rather, you know, it would be interesting to me to try and extend this to higher sort of Cass-Whitney number. Because for instance, you know, like, okay, so here's maybe what I would rather say. So Oliver Singh also has a paper too, where he sort of thinks, not so much about sort of the Cass and Whitney number, which I think of kind of like almost like right, like you can sort of do however many you want at once, but he sort of just thinks of like a length of a regular homotopy, I guess, like he's trying to do like only a few things at once. But yeah, if you had a regular homotopy from one thing to another where you only had to do sort of one finger and one Whitney move at a time, we would be really happy. But it's kind of an issue when you have to do 2 or more at a single time. So right, something that would be nice to know is sort of like, how skinny can you make a regular homotopy? So, if you have a regular homotopy, maybe you need n finger moves and n Whitney moves or something. So the Cass and Whitney number is high, but that doesn't necessarily mean you couldn't like do them all in a sequence. Or at least, maybe even do 2 at once or something like that. So something like that would be interesting to know and would like may or may not kind of help you extend this stuff to higher unknotting numbers.
One thing to note is that I think in a paper by Zemke, he proves that the roll spins all have width 2, right?
I think so. And you, Josh.
Any further questions?
Yeah, very quick question, Hannah. Do you know off the top of your head which of Kyle's papers gives the proof using surf theory that you can achieve a Glock twist by a log1 torus transform?
Wait, say it again. Say it again.
So if you scroll up, you somewhere.
Oh, Kyle
you
Larson.
gave,
Yeah.
Kyle Larson.
I don't remember.
Thanks.
I don't remember. But if you look at me and Patrick's paper, we cite his paper, so I can probably find it for you really quickly. Yeah.
Surgery on Tori. Yeah, perfect.
Cool.
I think Maggie just put it in the chat.
Yeah, I saw.
So great. Thank you.
Doesn't Kyle cite Gomph though?
I don't remember. But I mean, like, even initially this was due to Montesinos.
Right. All right, well, great. Let's thank Hannah again for a great talk.
Thank you, guys.